To move further, let me define so-called locally Minkowskian reference system or reference frame. It is such a reference frame in a vicinity of a point x0 which has the following property, that we choose a coordinate system such that in the vicinity of this guy, g mu nu of x0 is eta mu nu plus corrections, some corrections which I'm going to specify a bit later, and gamma mu nu alpha around that point is 0 plus some corrections. So the idea, it doesn't necessarily mean that the derivatives of g or gamma are also vanishing at this point. But the idea of this reference frame, reference system, is very simple. Suppose we have any curved space, like any curved space, but in a vicinity of any point, when the vicinity is very small, the space looks almost as flat. Almost means that there are corrections, but it looks almost as flat. And then, in that flat fraction of this space, we can specify some coordinate system. Because it's almost flat, we can choose locally Minkowskian reference system, where the metric is like that, and this guy is 0. So this is just a simple idea lying behind this thing, but let me explain mathematically how one can do this fixing. So, suppose we have two reference systems in the vicinity of this point. They are regional, k, and another one, k bar. Let me choose for both of this reference system the origin at x0 and introduce the coordinate xi, which is x minus x0, and xi bar, which is x bar minus x0. Then I do a coordinate transformation from xi to xi bar. It means that xi bar is a function of xi. And because I'm in the vicinity, small vicinity of this point, I can do a Taylor expansion of this guy, which means that xi mu, as a function of xi, is a mu nu times xi nu plus 1/2 b mu nu alpha xi nu xi alpha plus of order of xi cube. So this is now using the transformation rule for the metric. It is not hard to see that g bar alpha beta as a function of x0 is transformed as follows: a mu alpha, a nu beta, g mu nu of x0 plus of order of xi. Well, this just follows from the transformation rule of the metric when I care only about terms which are and neglect the terms which are higher in powers than xi. So keep only the leading term. The transformation rule for gamma is as follows: gamma alpha beta gamma as a function of x0 is equal to a alpha mu a nu beta a sigma gamma gamma mu nu sigma of x0 minus b, so it's minus, this is a continuation of b alpha mu nu a mu beta a nu gamma plus of order of xi. Notice that from this fact b is symmetric. B nu alpha is equal to b mu alpha nu. That one has to bear in mind. Now, it is not hard to see that this guy, this matrix, is a 4x4 matrix, so it has 16 components. A has 16 components. this guy is symmetric to 4 by 4 matrix. So G has 10 components. So of course, using these 16 guys, we can fix 10 components of this to be equal at alpha beta. That's exactly what is said here. So we transformed the original reference system where this guy was complicated function to such guy up to, of course, corrections. Up to corrections. It's better to say that not this guy is equal to at alpha beta, but this guy is equal to at alpha beta plus corrections. So what are the remaining 6 transformations? It's very simple. This metric has isometries, has such transformations which do not change it. These are Lorentz boosts, rotations, etc., etc., and there are 6 of them which keep this form of the metric. So this is perfectly clear. Also, so there's 3 Lorentz boosts, 3 rotations which keep this guy. And also, if we choose B alpha mu nu to be equal to A alpha gamma, gamma, gamma mu nu of x0, we also can set, up to these terms, we also can set this quantity to be 0. So when it is possible to do that, it is possible to do that when gamma is symmetric in these indices. It is possible to do that because this guy is symmetric in its lowercase indices. So let us look more closer to what is going on. Consider so-called torsion. Torsion is just the difference of 2 gammas. Gamma mu nu alpha minus gamma mu alpha nu. So despite the fact that this guy and this guy do not transform as tensors, remember in their transformation rule there is a part which makes it different from a tensor, but the difference between these 2 guys does transform as a tensor. One can check it by explicitly looking at the expressions how these guys are transforming. So this guy does transform as a tensor. So now if we can fix a reference frame where gamma is 0, then this guy is 0 in that locally Minkowskian reference system. But because this is a tensor, it means that it transforms multiplicatively. So it multiplies by something. So if it is 0 in one reference frame, and run a reference system, then it is 0 in any other. But now one can see that if it is 0, it means that gamma mu nu alpha is symmetric. So which is in accordance with what I have just said here. So the manifolds where the torsion is 0, where gamma is symmetric, and where one can use locally Minkowskian reference system, these manifolds are in literature referred to as Riemannian. So we continue with the definitions of related to curved spacetimes, to geometry, Riemannian geometry. So let me stress that metric tensor G mu nu and curvature gamma mu nu alpha are not independent. They are interrelated for Riemannian manifolds at least. So let us see how it happens. Consider the following covariant derivative of differential of a vector A mu. So one can write it like this: d alpha G mu nu A nu. So using just the definition of this guy. So and this, if we use Leibniz rule, this is just d alpha G mu nu times A nu plus G mu nu d alpha A nu. But to have an agreement between different definitions and to have in mind that this is a tensor quantity, we have to have that this is 0. In fact, this is a tensor quantity. something like T alpha mu. And we agreed that we can lower and higher indices with the use of the metric. Then, to have this equal to this, we have to have this to be 0. As a result, it means that metric has to be covariantly constant. G mu should be 0. This is very important relation, which establishes relation between metric and connection. Let me write this equation like this. D alpha, well, let us just use the definition of the covariant derivative. D alpha G mu nu is minus gamma mu nu alpha minus gamma nu mu alpha. This is just vertical line, slash. Here I just use the definition of the covariant derivative, and I use the multiplication of gamma to the metric tensor such that I lowered some of the indices. Now, we can write this relation in different manner by just reshuffling the indices. So it means that I can write another equation, which is d nu g alpha mu minus gamma alpha mu nu minus gamma mu slash alpha nu. This is another way of writing the same equation, and there is a third way. Let me write it here. 0 is equal to d mu g nu alpha minus gamma alpha nu mu minus gamma nu alpha mu. So we get 3 equations, actually on 3 quantities. We have to use the symmetricity property of this guy. As we know, this guy is symmetric. So then we have algebraic equation on gamma. So we can solve these 3 equations with respect to gamma to obtain the following equation for gamma. Gamma alpha mu nu is nothing but 1/2 of d nu g alpha mu plus d mu g nu alpha minus d alpha g mu nu. So, or gamma with uppercase index alpha mu nu is just 1/2 g alpha beta d nu g beta mu plus d mu g nu beta minus d beta g mu nu. Now we see that this connection gamma is nothing but the Christoffel symbol that have appeared in the previous lecture, at the very end of the previous lecture, where we found it appearing in the equation for the geodesic, for the extremal world line in space-time. So this is just nothing but Christoffel symbol. Moreover, as byproduct, we obtain another interpretation of the geodesic equation. Just to remind you, geodesic equation looks like this. It's just d over ds of a mu plus gamma mu nu alpha a u nu u alpha equals to 0. But this thing can be written as z dot nu d over dz nu. I mean, this derivative can be written like this. But this is nothing but u nu d over dz nu. But then this whole equation can be written as a result in the following form. It's u nu of s d nu of u mu of s equals to 0. So this is a geodesic equation. This is another form of the geodesic equation. And this just means that we have the following thing. We have a geodesic. We have a tangent vector to it. We take its covariant derivative, this, and then project on itself, on the tangent vector to the geodesic. So geodesic equation just has the following geometric meaning, that tangent vector to the geodesic is covariantly constant along the geodesic. That's the meaning of the geodesic equation that we have now.